Okay, in class I wrote down these numbers and asked people which of these numbers represented the number of dollars that flows through the U.S. economy in a day. How many dollars in a day? And a lot of people said, well, probably about 10 to the 40th. Some people said maybe 10 to the 13th or 10 to the 11th. It turns out, of course, that 10 to the 40th is an inconceivably large number. If we had that many dollars, our dollars wouldn't be worth anything. 10 to the 40th is kind of like the number of drops of water in the ocean, or the number of grains of sand in the Sahara. Turns out that the number is really closer to probably 10 to the 11th, although 10 to the 11th might be a little bit high. 10 to the 11th is 100 billion. 10 to the 9th is a billion. Okay? If we had $100 billion a day, 365 days a year, that would give us $36 trillion in a year. I don't think our economy is quite that productive yet, but it's getting there. It's more in the order of 10 trillion. But still, the number is kind of on the order of 10 to the 10th, 10 to the 11th. It's more than 10 to the 10th, less than 10 to the 11th. So 10 to the 40th is actually, well, let's think about this. 10 to the 13th is 10,000 times 10 to the 9th, because we'd multiply 10 to the 9th by 10 to the 4th, or 10,000, in order to get 10 to the 13th, because we had exponents. So this is 10,000 of these. So this number is a lot bigger compared to this than it looks like just from the exponents. We've got to keep that in mind. Turns out that you get up to 10 to the 80th or so, and you're getting close to the number of particles in the entire known universe, number of subatomic particles. Okay, we want to look at bases. The number 527 is 5 times 10 to the 2nd plus 2 times 10 to the 1st plus 7 times 10 to the 10th. 527 base 8 means 5 times 8 to the 2nd plus 2 times 8 to the 1st plus 7 times 8 to the 0. This 8 here says instead of using 10 like we did up here, we're going to use 8. Now, of course, if we're in a base 8 system, we don't want any numbers bigger than 8. We don't even want an 8. Just like in a base 10 system, we're never going to write 10 as one of our digits. However, there are systems that go over 10, like the hexadecimal system, base 16. Okay, hexadecimal, everything's times the power of 16. So 5A3B, what does that mean? Well, this is times 10 to the 0, or times 16 to the 0, times 16 to the 1, times 16 to the 2, times 16 to the 3. We have 5 times 16 to the 3, plus A times 16 to the 2nd, whatever A means, and we'll get to that in a minute, plus 3 times 16 to the 1st, plus B times 16 to the 0. Okay? Now, what's A and B mean? Well, if we've got a base 16, we've got to have 16 digits. Okay, the digits can run 0 through 9, but that's only 10 of them. So we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've only got 10 digits so far. We need 16. The next number would be 10. We can't use 10 for digits, so we call it A. The next number is 11. B is going to stand for 11. And then C, D, E, and F will stand for 12, 13, 14, and 15. Then we'll have 16 digits. Now, with that convention, knowing now that A stands for 10, we see that A times 16 to the 2nd is 10 times 16 to the 2nd. B times 16 to the 0, B is 11. So we have 11 times 16 to the 0. So that when we add these up, I don't have the actual number here. Let's see, 16 cubed is 4,096, 16 squared is 252, 16 is 16, and 16 to the 0 is 1. So you take 5 times 4,096, and so on, and you get the number for 5A3B hex expressed in decimal notation. 324 base 5, what's that mean? It means 3 times 5 to the 2nd plus 2 times 5 to the 1st plus 4 times 5 to the 0. We start here, we know this is a 0 power, then this is a 1st, this is a 2nd. So we move actually from right to left, building up from the 0 power. Now here's a question, and you should think about this before we look at the next clip. 527 equals what number to the base 5? How would we represent, what base 5 number would represent the decimal number 527?